Superposition. When two or more waves are in phase with each other, you can lay them on top of each other and it'll look or appear to be exactly one wave. For instance, in this top diagram, we have a blue wave and a pink wave laid on top of each other. These two waves are perfectly in phase, so they can combine and they look identical to each other. Meanwhile, if they're slightly out of phase, then we can see there's separation between these blue waves and the pink waves. This is called a phase difference. If the waves are completely out of phase, then you'll see that they are exactly in the opposite place at the same exact time. When waves are in phase with one another, and they're moving along, as in we had a wave moving from one end of a slinky to a wave moving to the other end of the slinky, when they were moving towards each other, they combine, and we got a greater amplitude than we normally had. When the waves are out of phase, then it just looks like this big mess. It's not this nice sinusoidal pattern. Here I have three waves happening all at once, and this animation can be confusing. So let me tell you about this black wave, this biggest black wave here. This black wave begins being formed when it is at 0 degrees or 360 degrees. And then as this black arrow moves counterclockwise, when it gets to 180 degrees, then it's going to be at its maximum negative displacement. When it's at 270 degrees, then it's back to equilibrium. 360, it's going to be at its maximum positive. 90, it's going to be back to equilibrium. You'll see that in just a second. Then we also have a green arrow, a green vector, and a blue vector, also going around this circle. And if we are plotting the displacement versus the angle, or the displacement versus time of these vectors, then we get this sinusoidal graph. So here it is in motion. At 360 degrees on the circle, that's also equal to 0 degrees. So that's where the wave will begin to form. If you look at this black arrow, as soon as the black arrow gets to that 360, we're at the maximum displacement in the positive direction. Once we get to 180 degrees over here, that's the maximum negative displacement. I'm showing you this only because this is a really interesting animation where you can see three different vectors, the red, blue, and green, representing three different waves, the red, blue, and the green. Whenever the black arrow is over top of one of these other vectors, that is the moment that it is in phase with another. And you can see that on the moving chart above me. This representation of a wave and being linked to a circle is pretty important because when you're moving around a circle, it is essentially just this. So you can imagine if you sliced the circle right here at this 270 mark, and then you just laid it over top of this. This entire wavelength is going to equal 2 pi radians, as noted down here. All right, so it does not matter where the 0 degree or 360 degree is. For instance, if we put 360 up here at the very top, then that could also make sense because then we're starting at the equilibrium, and then this would be maximum displacement, equilibrium, maximum displacement again. But the idea is if we shine a light around or at an object that was going in a circle, this is the pattern it would be making. Again, if two waves are in phase, they add together. If they're out of phase, then they subtract one another. You can slow down the animation on YouTube so you can see this a little bit clearer, but here we have waves moving in opposite directions and they're interacting with each other, sometimes making larger crests and sometimes canceling each other out when they're out of phase.